Rogue planet. A rogue planet, also termed a free-floating planet, FFP, or an isolated planetary mass object, IPMO, is an interstellar object of planetary mass which is not gravitationally bound to any star or brown dwarf. Rogue planets may originate from planetary systems in which they are formed and later ejected, or they can also form on their own, outside a planetary system. The Milky Way alone may have billions to trillions of rogue planets. The upcoming Nancy Grace Roman Space Telescope will likely be able to narrow. Some planetary mass objects may have formed in a similar way to stars, and the International Astronomical Union has proposed that such objects be called sub-brown dwarfs. A possible example is CHA 110,913-773,444, which may either have been ejected and become a rogue planet or formed on its own to become a sub-brown dwarf. Terminology. The two first discovery papers use the names isolated planetary mass objects, IPMO, and free-floating planets, FFP. Most astronomical papers use one of these terms. The term rogue planet is more often used for microlensing studies, which also often uses the term FFP. A press release intended for the public might use an alternative name. The discovery of at least 70 FFPs in 2021, for example, used the terms rogue planet, starless planet, wandering planet and free-floating planet in different press releases. Discovery. Isolated planetary mass objects, IPMO, were first discovered in 2000 by the UK team Lucas and Roche with Euclid in the Orion Nebula. In the same year the Spanish teams Zapatero Osorio et al. Discovered IPMOs with Keck spectroscopy in the Sigma Orionis cluster. The spectroscopy of the objects in the Orion Nebula was published in 2001. Both European teams are now recognized for their quasi-simultaneous discoveries. In 1999 the Japanese team Oasu et al. Discovered objects in Chameleon I that were spectroscopically confirmed years later in 2004 by the US team Lumen et al. In October 2023, based on observations of the Orion Nebula with the James Webb Space Telescope, astronomers reported the discovery of pairs of rogue planets, similar in mass to the planet Jupiter, called Jupiter mass binary objects, jumbos. Observation. There are two techniques to discover free-floating planets: direct imaging and microlensing. Microlensing. Astrophysicist Takahiro Sumi of Osaka University in Japan and colleagues, who form the microlensing observations in astrophysics and the optical gravitational lensing experiment collaborations, published their study of microlensing in 2011. They observed 50 million stars in the Milky Way by using the 1.8 meter, 5 feet 11 in, MOA-2 telescope at New Zealand's Mount John Observatory and the 1.3 meter, 4 feet 3 in, University of Warsaw telescope at Chile's Las Campanas Observatory. They found 474 incidents of microlensing, 10 of which were brief enough to be planets of around Jupiter's size with no associated star in the immediate vicinity. The researchers estimated from their observations that there are nearly 2 Jupiter mass rogue planets for every star in the Milky Way. One study suggested a much larger number, up to 100,000 times more rogue planets than stars in the Milky Way, though this study encompassed hypothetical objects much smaller than Jupiter. A 2017 study by Przemysław Mraz of Warsaw University Observatory and colleagues, with 6 times larger statistics than the 2011 study, indicates an upper limit on Jupiter mass free-floating or wide-orbit planets of 0.25 planets per main sequence star in the Milky Way. In September 2020, astronomers using microlensing techniques reported the detection, for the first time, of an Earth mass rogue planet, named Ugal 2016 BLG 1928, unbound to any star and free-floating in the Milky Way galaxy. In December 2013, a candidate exomoon of a possible rogue planet, MOA 2011 BLG 262, was announced. Direct imaging. Microlensing planets can only be studied by the microlensing event, which makes the characterization of the planet difficult. Astronomers therefore turn to isolated planetary mass objects, IPMO, that were found via the direct imaging method. To determine a mass of a brown dwarf or IPMO, one needs, for example, the luminosity and the age of an object. Determining the age of a low-mass object has proven to be difficult. It is no surprise that the vast majority of IPMOs are found inside young nearby star-forming regions of which astronomers know their age. These objects are younger than 200 ms, are massive, greater than 5 megajoules, and belong to the L&T dwarfs. There is, however, a small growing sample of cold and old white dwarfs that have estimated masses of 8 to 20 megajoules. Nearby rogue planet candidates of spectral type Y include WISE 0855-0714 at a distance of 7.27 ± 0.13 light-years. If this sample of white dwarfs can be characterized with more accurate measurements, or if a way to better characterize their ages can be found, the number of old and cold IPMOs will likely increase significantly. The first IPMOs were discovered in the early 2000s via direct imaging inside young star-forming regions. These IPMOs found via direct imaging formed probably like stars, sometimes called sub-brown dwarf. There might be IPMOs that form like a planet, which are then ejected. These objects will, however, be kinematically different from their natal star-forming region, should not be surrounded by a circumstellar disk, and have high metallicity. None of the IPMOs found inside young star-forming regions show a high velocity compared to their star-forming region. For old IPMOs, the cold WISE J0830 plus 2837 shows a FTN of about 100 km per second, which is high, but still consistent with formation in our galaxy. For WISE 1534 to 1043, one alternative scenario explains this object as an ejected exoplanet due to its high FTN of about 200 km per second, but its color suggests it is an old metal-poor brown dwarf. Most astronomers studying massive IPMOs believe that they represent the low-mass end of the star formation process. Astronomers have used the Herschel Space Observatory and the Very Large Telescope to observe a very young free-floating planetary mass object, OTS-44, and demonstrate that the processes characterizing the canonical star-like mode of formation apply to isolated objects down to a few Jupiter masses. Herschel far-infrared observations have shown that OTS-44 is surrounded by a disk of at least 10 Earth masses, and thus could eventually form a mini-planetary system. Spectroscopic observations of OTS-44 with the Symphony spectrograph at the Very Large Telescope have revealed that the disk is actively accreting matter, similar to the disks of young stars. Jupiter mass binary objects. In the Orion Nebula, a population of 40 wide binaries and 2 triple systems were discovered. This was surprising for 2 reasons. The trend of binaries of brown dwarfs predicted a decrease of distance between low-mass objects with decreasing mass. It was also predicted that the binary fraction decreases with mass. These binaries were named Jupiter mass binary objects, jumbos. They make up at least 9% of the IPMOs and have a separation smaller than 340 astronomical units. It is unclear how these jumbos formed, but an extensive study argued that they formed in situ, like stars. If they formed like stars, then there must be an unknown extra ingredient to allow them to form. If they formed like planets and were later ejected, then it has to be explained why these binaries did not break apart during the ejection process. Future proper motion measurements with JWST might resolve if these objects formed as ejected planets or as stars. Ejected planets should show a high proper motion, while a formation like stars should show proper motions similar to the trapezium cluster stars. Other suspected jumbos are known outside the Orion Nebula, such as 2-mass J11193254113746 AB, 2-mass J15530222 plus 153236 AB, WISE 1828 plus 2650, WISE J0336-0143, could also be a brown dwarf and a planetary mass object, BD plus PMO, binary, and 2-mass J0013-1143. Total number of known IPMOs. There are likely hundreds of known candidate IPMOs, over 100 objects with spectra, and a small but growing number of candidates discovered via microlensing. Some large surveys include, as of December 2021, the largest ever group of rogue planets was discovered, numbering at least 70 and up to 170 depending on the assumed age. They are found in the OB association between Upper Scorpius and Ophiuchus with masses between 4 and 13 megajoules and age around 3 to 10 million years, and were most likely formed by either gravitational collapse of gas clouds, or formation in a protoplanetary disk followed by ejection due to dynamical instabilities. Follow-up observations with spectroscopy from the Subaru telescope and Gran Telescopio Canarios showed that the contamination of this sample is quite low, less than or equal to 6%. The 16 young objects had a mass between 3 and 14 megajoules, confirming that they are indeed planetary mass objects. In October 2023, an even larger group of 540 planetary mass object candidates was discovered in the Trapezium cluster and Inner Orion Nebula with JWST. The objects have a mass between 13 and 0.6 megajoules. A surprising number of these objects formed wide binaries, which was not predicted. Formation. There are in general two scenarios that can lead to the formation of an isolated planetary mass object, iPMO. It can form like a planet around a star and is then ejected, or it forms like a low-mass star or brown dwarf in isolation. This can influence its composition and motion. Formation like a star. Objects with a mass of at least 1 Jupiter mass were thought to be able to form via collapse and fragmentation of molecular clouds from models in 2001. Pre-JWST observations have shown that objects below 3 to 5 megajoules are unlikely to form on their own. Observations in 2023 in the Trapezium cluster with JWST have shown that objects as massive as 0.6 megajoules might form on their own, not requiring a steep cutoff mass. A particular type of globule, called globulates, are thought to be birthplaces for brown dwarfs and planetary mass objects. Globulates are found in the Rosette Nebula and IC 1805. Sometimes young iPMOs are still surrounded by a disk that could form exomoons. Due to the tight orbit of this type of exomoon around their host planet, they have a high chance of 10 to 15% to be transiting disks. Some very young star-forming regions, typically younger than 5 million years, sometimes contain isolated planetary mass objects with infrared excess and signs of accretion. Most well known is the iPMO OTS-44 discovered to have a disk and being located in Chamaeleon I. Chamaeleon 1 and 2 have other candidate iPMOs with disks. Other star-forming regions with iPMOs with disks or accretion are Lupus I, Rho Ophiuchi Cloud Complex, Sigma Orionis Cluster, Orion Nebula, Taurus, NGC 1333 and IC 348. A large survey of disks around brown dwarfs and iPMOs with ALMA found that these disks are not massive enough to form Earth-mass planets. There is still the possibility that the disks already have formed planets. Studies of red dwarfs have shown that some have gas-rich disks at an relative old age. These disks were dubbed Peter Pan disks, and this trend could continue into the planetary mass regime. One Peter Pan disk is the 45-year-old brown dwarf 2-mass JO2265658532732 with a mass of about 13.7 megajoules, which is close to the planetary mass regime. Formation like a planet. Ejected planets are predicted to be mostly low mass, less than 30 me. Figure 1 Ma et al., and their mean mass depends on the mass of their host star. Simulations by Ma et al. did show that 17.5% of 1M stars eject a total of 16.8 me per star with a typical, median, mass of 0.8 me for an individual free-floating planet, FFP. For lower mass red dwarfs with a mass of 0.3 m, 12% of stars eject a total of 5.1 me per star with a typical mass of 0.3 me for an individual FFP. Hong et al. Predicted that exomoons can be scattered by planet-planet interactions and become ejected exomoons. Higher mass, 0.3 to 1 megajoule, ejected FFP are predicted to be possible, but they are also predicted to be rare. Fate. Most isolated planetary mass objects will float in interstellar space forever. Some iPMOs will have a close encounter with a planetary system. This rare encounter can have three outcomes. The iPMO will remain unbound, it could be weakly bound to the star, or it could kick out the exoplanet, replacing it. Simulations have shown that the vast majority of these encounters result in a capture event with the iPMO being weakly bound with a low gravitational binding energy and an elongated highly eccentric orbit. These orbits are not stable and 90% of these objects gain energy due to planet-planet encounters and are ejected back into interstellar space. Only 1% of all stars will experience this temporary capture. Warmth. Interstellar planets generate little heat and are not heated by a star. However, in 1998, David J. Stevenson theorized that some planet-sized objects adrift in interstellar space might sustain a thick atmosphere that would not freeze out. He proposed that these atmospheres would be preserved by the pressure-induced far-infrared radiation opacity of a thick hydrogen-containing atmosphere. During planetary system formation, several small protoplanetary bodies may be ejected from the system. An ejected body would receive less of the stellar-generated ultraviolet light that can strip away the lighter elements of its atmosphere. Even an Earth-sized body would have enough gravity to prevent the escape of the hydrogen and helium in its atmosphere. In an Earth-sized object, the geothermal energy from residual core radioisotope decay could maintain a surface temperature above the melting point of water, allowing liquid water oceans to exist. These planets are likely to remain geologically active for long periods. If they have geodynamo-created protective magnetospheres and seafloor volcanism, hydrothermal vents could provide energy for life. These bodies would be difficult to detect because of their weak thermal microwave radiation emissions, although reflected solar radiation and far-infrared thermal emissions may be detectable from an object that is less than 1,000 astronomical units from Earth. Around 5% of Earth-sized ejected planets with Moon-sized natural satellites would retain their satellites after ejection. A large satellite would be a source of significant geological tidal heating. List. The table below lists rogue planets, confirmed or suspected, that have been discovered. It is yet unknown whether these planets were ejected from orbiting a star or else formed on their own as sub-brown dwarfs. Whether exceptionally low-mass rogue planets, such as Ogle 2012 BLG 1323 and KMT 2019 BLG 2073, are even capable of being formed on their own is currently unknown. Discovered via direct imaging. These objects were discovered with the direct imaging method. Many were discovered in young star clusters or stellar associations, and a few old are known, such as WISE 0855-0714. List is sorted after discovery year. M.J. Milley. Discovered via microlensing. These objects were discovered via microlensing. Rogue planets discovered via microlensing can only be studied by the lensing event and are often also consistent with exoplanets in a wide orbit around an unseen star.